Okay, let's start. तंजीब,
अस्सलाम वालेकुम सर।
कि स्टूडेंट्स कहाँ हैं आप?
सर पता नहीं, अब इतने ही आते हैं।
सभी क्लासेस में?
सर हाँ, लगभग इतने ही, 30 तक, ज़्यादा से 30 32 तक।
बाकी कहाँ हैं? वेयर आर दे?
पता नहीं, शायद वो नहीं देते हैं क्लास।
उनको बोलना आज ये वो डिटेन हो जाएंगे।
ठीक है।
पहले तो 40 थे, आप 45 भी आते थे।
यस सर, पहले दिनों 45 48 आते थे।
तो आज एप्लीकेशन सबमिट कर दी थी ना।
उसके बगैर भी रोल इज लेसर, 5 6 दिन
सर
से
उसके
मिलेंगे।
बगैर भी लगभग 28 30 स्टूडेंट्स तक आते हैं बस।
Okay. Anyway, let's start. So we'll be doing uh, revision of this typical test signals. So next is our typical test signals, the commonly used test signals. We know they are step, ramp, and parabola and impulse. So first is a step function. We already know, we have studied in the network analysis about the step function. So step function represents what? Represents an instantaneous change in the reference input. That means it will step to some value. Maybe it's a unit step. It can go to any k value or some other value. So step function represents what? It represents an instantaneous change in the reference input. Step function represents an instantaneous change in the reference input. Okay, input. Now, mathematically, if we write the description of the step function, mathematical description of step function of magnitude k, can have any magnitude. So step function we can write like this. Can show it mathematically also. First I will draw the graph like this. So step, I can take a step of this any magnitude here. Okay, so this is your input and this is your time signal, and this is r of t will be k u of t. So mathematically, when that is valid, you already know r of t will be equal to value k when it will be for t greater than 0. So for t less than 0, this does not exist. This is a mathematical equation of this one that you already know. So you can have a unit step when k will be of magnitude 1, can have a unit step, and then t greater than 0, k will be 1. That you can interpret later. So Laplace, if we find the Laplace transform, we have already done it, I think, Laplace transform also. But so Laplace transform of any function, we know mathematically it is 0 to infinity f of t e to the power minus st dt. Now f of t here is 0 to infinity k u of t. Here the function is k u of t. Now k we will take outside. U of t, let's take this u of t as 1 unit step. So k, then the, sorry, this is minus cfst here multiplied for the definition. Then it will be integration of this is minus s from 0 to infinity, and that we know k e raised power of minus infinity upper limit minus as you can take here minus e raised power of 0 e raised power infinity is 0 k by s anything raised power 0 is 1 so this is minus here so we can say that Laplace transform of a unit step function with a magnitude k can be written as k divided by s. But if the value of k is 1, then it is simply a unit step function. So Laplace transform of a unit step function, that means we have taken this unit step function is 1 by s. We have done it in network analysis also. So if we have to see the physical significance of this one, step function is also called displacement. It's also called displacement. Okay, displacement function. Step function can be described certain application of input signal to system. So we can write what R of S is 1 by S. So certain input you have to apply. If a signal, we require a test signal, whether we have to use a certain input, then step is the best signal for that one. So this is number one. Number two is your ramp function. Ramp function. So ramp function, we know ramp function is a function that changes constantly with time. Is a function that changes constantly with time. That you know already. The mathematical description of ramp function is like this. So ramp function, we can say if this is input, R of t is given as k of t for t greater than 0, and then it can have 0 for t less than 0. This is k of t. Now, okay. Now, how we can draw the ramp function? You can draw it like this. Okay, now this is ramp function time t. Now here it is R of t, and this is slope, we say k, and this is our x is k greater than 0, that we know already. Now we need to find the Laplace transform of this one. Now Laplace transform of R of t will be equal to 0 to infinity r of t e raised to power minus st dt, which further can be written as 0 to infinity. R of t is what? T, k of t. So it is power minus st dt, and this we know we can write it integration by parts. So first we will consider t 0 to infinity e raised to power minus st dt minus whole integral 0 to infinity. Differentiation of first differentiation of t is 1. This is integration by parts. Everybody know. I don't need to explain this. E raised to power minus st dt, and this whole will have a dt. Okay. So this further can be written as k. So this is t e raised to power minus st minus s 0 to infinity minus 0 to infinity 1, that will be e raised to power minus st divided by minus s dt. Okay, this limit we have to apply to whole. This t is also involved in this limit. Sorry, we have to apply this limit whole. Just a second. This I should rub it. Okay. So this will become, this part is going to become, this k is multiplied to all. Okay. So this part is going to become 0, 0 in this case, and this will be minus 0 to infinity. This will be plus 1 by s. And if we take the integral of this again, minus e raised to power st minus s. Okay. Yeah, this is going to be plus, and this is minus 0 by st, and this limit is from 0 to infinity. Now here k is outside, and this is going to become 1 by s, and minus s square minus 1 by s. We can solve this limit. E raised to power minus infinity e raised to power 0, and this is going to become k minus was 1 by sk s square, sorry. E raised to power infinity is 0, e raised to power 0 is 1, and this is going to become, sorry, okay, this is going to become limit, sorry, Laplace transform of ramp function is going to become k divided by s square. So for unit ramp, if we have to go for unit ramp, k is equivalent to 1, that will be 1 by s square. If the input to the control system are generally changing functions, so if we have a changing function that's instantaneously changing at different instance, then it is better to use the ramp function as a test signal. So if input to a control system are generally a changing function with respect to time, then a ramp function is a suitable or a good test signal. So appropriately we will use the, if input is like this, then we will use the test signal. Then third is our parabolic. Parabolic function. Okay. Parabolic function represents one order faster than ramp function. It sorry. It represents a signal that is one order faster than the ramp function. So that we already know, we have seen this in network. So mathematically, parabolic function description can be written as, so that is because one order faster as compared to ramp, so we have to write k t square by 2. It's only valid for t greater than 0, rest it's not valid. T less than 0, it will be 0. So here we can write r of t is kt square by 2 into u of t. Now if we draw this function, okay, then parabolic will be something like this. Okay, so that means here r of t will be kt square by 2 into u of t, that is the time t, and that is your input function. So this you can derive. I will write the result only, don't want to waste the time. Integration you can do r of t multiplied by e raised to power minus st for Laplace transform, and rs will be 0 to infinity kt square by 2 multiplied by e raised to power minus st. Again we have to go by integration by parts, and the result of this is k by s cube. So if k is 1, then it will be 1 by s cube. Fourth is, I think you can do this integration, you can solve this integration. This is a simple mathematics from here. Fourth function is the impulse function. Okay. The impulse function also I have explained this in detail in case of network analysis. So we can draw the impulse function graph. So impulse function input is impulse. We represent that by delta t is 1. It is valid only at origin. The rest other it's not valid. Exists only at the origin. So impulse function is defined as, in mathematical terms, it is defined as if r of t is impulse function, it will be 1 at origin equal to 0. Rest it's not valid. It will be 0. Okay, otherwise it is 0. On origin it will be 1. Okay. The function has what? The function has a unit value for only t equal to 0. In practicals, we can have a pulse width like anything 1a or 1 by a, can multiply that and we can get a unit impulse function. So we don't need to get details of that one. Let's talk about the Laplace transform. I think this also I have explained and we have derived in network analysis. But for your information, delta t, let's say, is u of t. That means it's valid at t equal to 0. Let's say it's a u of t. Let delta t Laplace transform of delta t, okay, is L by dt of u of t. So we will differentiate this u of t, okay. Then this Ls d by dt is s. So this is Ls. Then it is unit step function. Okay. Laplace transform of unit step is, what is this? Sorry. Just a second. I should have written like this. Okay. This is S for this operator, Laplace transform of, for operator d by dt is S. We know this already. Laplace transform u of t. Laplace transform of u of t is what? It is 1 by S. So Laplace transform of impulse is, in the short form, it is 1. Laplace transform of impulse function delta t is 1. Explanation I have given in the network, so we don't need to go for the explanation here. Okay. Next topic is, this is just know the Laplace transform. Just I'm revising for the Laplace transform value, because we'll be using this value in the different test signals when we will apply inputs. Different inputs will be using this value. So next is poles of a transfer function. Poles of a transfer function. Now, if we talk about the poles of a transfer function, so clearly there are two parts of the definitions. There are two parts of the definition. The poles of the transfer function are poles of the transfer function are, number one, what are they? The values of the Laplace transform variable s of the Laplace transform variable s, because we'll be changing first that into Laplace transform variable s that cause the transfer function to behave, to become, rather, to become, the value becomes infinite. So whenever we are changing any polynomial into the Laplace transformer, then the value of the Laplace transform s that will make the transfer function to become infinite. Sorry, it's not finite, infinite. That will make it infinite. Or number two part of the definition is, okay, any roots of the denominator, okay, of the transfer function, any roots of the denominator of the transfer function that are common to the roots of the numerator. That are common to the roots of the numerator. So what is the meaning of this one? See, if I have a polynomial, a simple first order I am taking, s plus 9. Okay, this is the first part of the definition. Now, the values of the Laplace transform, because I have changed this in the Laplace transform, s plus 9 is this one. Values of the Laplace transform s that causes the transfer function to become infinite. So value of s, if we will take as minus 9, so this will become 1 by 0 and it will make it infinite. So this will be called as the pole of the transfer function. Very simple language. This will be called as the pole of the transfer function. Now, second part of the definition is, now if I have s plus 2 divided by s plus 9 divided by s plus 2. Now, any roots of the denominator of the transfer function that are common to the roots of numerator, these are two roots are common. S is equal to minus 2, s is, they will cancel off each other. But still, even though they cancel off each other, but still we consider this s is equal to minus 2 as the pole of the transfer function. Okay, this is the first two definitions. What is the meaning of these two in mathematical terms? Now, a bit more explanation. Now, if we strictly speak of, if we are strict in the practical terminology, then we say that the poles of the transfer function will satisfy part one. Satisfy part one of the definition. One of the definition, there is no problem. That is, for example, if we have roots of the characteristic polynomial, in the denominator are values of s that make the transfer function infinite. That means what I have shown example here, the polynomial is there. We are considering a root s is equal to minus 9. We are substituting here, and that will make, suppose there is a transfer function g of s here, that will make the value of this transfer function to go infinite. So this is, for this definition, we don't have any problem. However, if in second part of the definition, what we have, if a factor of the denominator, okay, if the factor of the denominator can be cancelled by the same factor in the numerator. But practical terms, what we see now, second, I have given example here. Second, that this root and this root of any transfer function, you can say this is g of s a transfer function. What is that? If factor of the denominator, okay, can be cancelled by the same factor in the numerator, then what will happen? The roots of the factor no longer cause the transfer function. Now here, the roots of these factors will no longer cause this transfer function to become infinite. So practically, if we speak about the definition, then it should not be included in the definition. Practically, if we speak, because these will cancel each other, numerator and denominator cancels each other, and roots of this will not cause this transfer function to become infinite. So practically speaking, this should not be included in the definition. But in control system, mostly in the literature of the control system, the cancelled roots of the denominator will be also treated as the roots of, will be also treated as the poles, even though the transfer function will not become infinite at that particular value. Hence, we include second part also of the definition. So it should be very clear. Somebody may ask the question, sir, why we are cancelling? But that's its significance and importance will come ahead. I will tell you why we are considering this also a pole. If we are considering this as a pole, that sometimes we will also this as a zero also. So this has to be included second part of the definition. Although, because these two will cancel off each other, but they don't make the transfer function to become, the value of the transfer function will not become infinite. Just a second. Office से phone. Hello. हाँ बिलाल सर हुई नहीं. हाँ मैंने दोनों किए. अच्छा अच्छा चलो वो करो कैश. चलो चलो चलो. Okay. So this is about the poles of it. Zeros of the transfer function will hold the same thing. Zeros of a transfer function. Okay. Zeros of the transfer function. Okay. Now same, what is the zeros of a transfer function are values of the Laplace transform variable s that causes the transfer function to become not infinite this time, it becomes zero. I will copy these two. Okay, let me copy these two definitions. I will just change them. Okay, I think let's copy. And this is paste. Okay. So the poles of the transfer function that are values of the Laplace transform are s, the not poles here. So we will be using here zeros. So zeros of the transfer function, transfer zeros of the transfer function are the values of the Laplace transform variable s that causes the transfer function to become not infinite but zero. So I will change this infinite to zero. Okay. Second definition, second part is any roots of the numerator. Now not denominator because we'll be considering the numerator. Any roots of the numerator of the transfer function that are common to the roots of the denominator. Okay. So here it is. Any roots of the numerator of the transfer function that are common to the roots. So same thing to the roots of the denominator. Same thing holds good here. So here I will take the same example. If I have s plus 8 divided by s plus 9 as a transfer function. G of s is a transfer function. Now, if I take s value equal to minus 8, so transfer function g of s will become 0. So first definition is the values of the Laplace transform variable s that cause the transfer function to become 0. So this is definitely a 0. Then let's say we have common roots in the numerator and this is s plus 8. Then we are having a common s plus 9 and s plus 9. Now s plus 9 and s plus 9 cancel off each other, numerator with the denominator, then we have value of s plus 8. Although this does not make the transfer function to become 0, but still we include this value in the definition of the zeros of the transfer function as we have included the pole. So part 2 of the definition is also included here. So what is there? In the control system, we often refer to the roots of the cancelled factor in the numerator as 0, even though the transfer function will not become 0 at this value. So, however, we will include this because there are reasons I will tell you once we will be doing our time domain analysis. We'll see what will have an effect of a pole and 0 there. So next is for the first order, poles and zeros of a first order system. Okay. Now let me draw a simple transfer function. Let's say this is g of s here, and the value of g of s is s plus 2 divided by s plus 5. And here the value of r of s is input is step, and this is your output c of s. If we have to draw the graph of this one, okay. Now if we have to draw the graph of this one, let us draw the graph. How we will drawing the graph this. Okay, now this axis is called sigma, imaginary axis. Okay. This lower axis is called a imaginary axis. Sorry, sigma. This is called a sigma, and this is imaginary axis. Real axis is sigma. This is minus sigma. This is, and this is minus imaginary. This is imaginary axis. How we draw for S plane. Okay, this is an sigma real axis, minus real axis, negative real axis, positive imaginary axis, negative imaginary axis. Now, First of all, what is the value we have? We have a pole at -2, we have a 0 at we have a 0 at -2 and pole at -5. So 0 at -2, how we will draw this? We'll draw this. Suppose this is the value here, -2, and pole we will represent by cross. It is pole represents cross, 0 represents 0. So this is your S plane. S plane will have what? S plane will have signal j omega. So now, if we explain this more precisely, these are three types of, okay, roughly I will write on it for this. This is just for explanation. Okay. Now, input pole. What is input pole in this system? Input pole is 1 by S. That's a step. See, input pole 1 by S. That means pole at origin. So input pole is, if we draw a graph about this, and if this is real axis sigma, this is imaginary axis, this is S plane, then we have pole at origin. Let me use another pen. Then we have pole at origin in this case. Now there are two system poles. See, transfer function means system pole. This means system pole, this means input poles. So system pole and input pole. System poles we have 1, system 0 we have 1. So 1 by 1. So first we will be writing system 0. That means for the transfer function system we'll write. So now here, if we draw the graph of this one, okay, again, this is your real axis sigma and imaginary axis jw. So where we have pole at -2. So I can draw it here -2. So we have S plus 2 actually is this one. So we have 0, 0 at -2. And this is your S plane again. This is S plane. Now third again will be system pole. System 0, and we have system pole also. System pole will be what? Let me draw it. It will be, okay, this is S plane. This is your real axis. This is your imaginary axis. This is S plus 5, I think. Yeah, S plus 5. System pole is at S plus 5. So that means S is equivalent to -5. So somewhere here we have this. Okay. So we will be drawing it -5. This is your pole. Let me change the pen color. This is your system pole. This is your system 0. This is your input pole. Okay. Now we have, in this case, what we have C of S. Output is equal to what? We already know transfer function is equivalent to G of S is equivalent to output by input R of S. So if we have to get output, that will be G of S into R of S. That we know already. We have seen this. So C of S we can write. How we can write it? C of S we can write 1 by S is the input, and okay, and G of S is S plus 2 divided by S plus 5. So output we can write here like this. This is very clear. We have seen this. This is input. This is transfer function. We can multiply this input and transfer function, and we can get the value of output. Now let's solve this. So this value 1 by S into S plus 5 here, we have into S plus 2 on the numerator. So we can write this in the partial fraction as a by s plus b by s plus 5. Now here we can write s plus 2 further as a s plus 5 and b we can write it as s. Okay, we multiply the denominator on the other side, so ss gets cancelled, here will be s plus 5, s plus 5 gets cancelled, here will be s. Now let us let s is equivalent to 0. If s is equivalent to 0, this will become 0, this will become 2, so we will have 2, this will become 0, and a multiplied by 5, so a will be 2 by 5. The value of a will be 2 by 5. Okay, now let s value is equivalent to minus 5 now. If s value is minus 5 plus 3 is minus 3, then b minus 5, so b value we can have 3 by 5. So b value will be getting as 3 by 5. Okay, then we'll substitute this in the equation number 1. So c of s will become, which is equal to s plus 2 divided by s into s plus 5, which is further equal to a by s plus b by s plus 5. Now we substitute these values here. C of s can be written as a 2 by 5 1 by s minus, not minus, plus, it will be 3 by 5 1 by s plus 5. So now taking the Laplace transform of this one, not Laplace transform, Laplace inverse. We know how to take the inverse. We have seen, we have, in case of network, we have done it. So C of t in time domain, we will get 1 by s is step is 1 plus 3 by 5, and this is e raised power minus 5t. This result is important for us for mathematical interpretation for physical significance. Okay, let's move further. So now we are taking this an example of the first order system. Okay, now from the development summarized from the equation number first, let's say this is equation number, sorry. From the equation number 1, what we have, we can consider following conclusions from we can draw following conclusions. Okay, Tanzib, it is okay or not? समझ आ रहा है कि नहीं?
Yes, sir, clear.
Okay. The number 1 is, we also studied this in the network, but I am just थोड़ा सा इसको और explain करते हैं. A pole of input function, first conclusion is a pole of input function generates what? It generates the form of forced response. So a pole of input function generates the form of the forced response. That is, the pole at the origin generates a step function at the output. So that's what is the meaning. The pole at the origin will generate what? Step function at the origin. So second is, so pole of input function will develop what? Forced response. The pole of the transfer function pole of the transfer function generates the form of natural response that is the pole at minus 5 generates e raised power minus 5t. So that's a natural response. So pole at what? The pole of the input pole will generate forced response, whereas the system pole or the pole of the transfer function will, in other words, it will generate the form of natural response. It will generate the form of the pole on the real axis, okay, generates an exponential response. Third is a pole on the real axis generates an exponential response. Generates an exponential response of the form e raised power minus alpha t, where minus alpha is the pole location. Where minus alpha is the, so real axis we will get that s is equivalent to s plus 5 or s minus 5, whatever we are getting. Once we take the Laplace inverse, that will generate an exponential response of the form we have seen just now, e raised power minus alpha. In this case, alpha t, alpha is the location of the pole. Now, it's very important the farther, that is at a distance, the farther to the left of the pole, farther to the left of the pole is on the negative real axis. You can very clearly see that. So if we move left of the pole here, farther to the left of the pole, if we move here, okay, which is again already on the negative axis, it will be on, we will be moving away from the negative axis, negative real axis rather. Okay. Now further at a distance, it will be the farther the exponential transient response will decay to. So if pole is farther to the left, that means it's at a distance on the left side of real axis, then faster, in this case, the faster the exponential transient response will decay to zero. So this is a very important valid point. Number one, I'll explain it further. Pole at the origin will generate a forced response. Pole on the real axis will generate a natural response. Now, pole on the real axis generates an exponential response that will be of the form that is a e raised power minus alpha t, where alpha is the location of the pole. Then if we have the pole farther to the left, that means it's at a distance and it's moving, it's away from the negative real axis. It's a very far away value from the negative real axis. Then the faster exponential, the very fast exponential transient response that will decay to zero. So that value, the response will decay to zero very fast in this case. This has to be remembered. Number fourth is zero and poles generate the amplitude of for both. That we can see. That's not a difficult point. So we'll write it here. The zeros and poles generate the amplitude for both forced and natural response. Forced and natural responses. So we'll see that amplitudes, how they are going to develop, how they are going to generate this type of, that we will see. And this can be seen from, we can see this from the calculations of A and B. That will be the amplitude in this case. Whatever the amplitude, the values of the partial fractions A and B will come, that will be amplitude. That we'll see in that case. In further details, we can see that. So next is first order system. Okay. Tomorrow we'll talk about the first order system. We'll have an introduction. First order system. Okay. First order system. A first order system means what? First of all, we should always know that first order system means in the denominator we will have a degree of 1. That's a first order. Second order will be defined like this. It's the same mathematical definition. A first order system, we can say, okay, a first order system, let's consider an example. First order system without zeros. First order system is there, but zeros are not there. Only there are poles. Can be described by the transfer function shown in figure. Let's see. Okay. Now, if the input is a unit step, we know what is unit step, where R of S will be 1 by S in Laplace transform. Okay. The Laplace transform of step response is C of S, that we can write here. You can see. Let's take an example. Okay. So let's say we have R of S, that is step, and we have G of S, that is transfer function, that is, let's say this is A by S plus A, and we have output, that is response, we call it output. Okay, we will draw the graph for this one also for explanation of the first order system. So this is your imaginary axis, and this is your sigma real axis, and this is your S plane. Now here, let's say this location is minus A, on the S is equal to minus A, that's a pole. So we have C of S is R of S into G of S, that we already know. So C of S will be R of S. We have said this is an input. Input is step. G of S is A by S plus A. Now let's first solve this one. C of S is equal to A divided by S into S plus A. Can be further written as A by S plus B by S plus A. Then we can write this A by S plus B by S plus A, multiply this multiply this with this denominator of this equation, a and a will get cancelled. Let me write it like this. Sorry. Okay, let me write it like this. So C of S will be now equal to a and a gets cancelled. So this will go on the other side. So this will be a into S plus a. Okay. A into S plus a, b into S. This is very clearly. So we substitute S is equivalent to 0. I'm writing fast. You can do it yourself also. S is equivalent to 0 if you put. So that will become, sorry, this is 1 here. Later on we can put it equal to this. 1 it will become, because a and it can cancel, that will go other side. A, S is equal to 0, so that will be 1. A, S is equivalent to 0, that will be a small a, and therefore a will be 1 by small a. Similarly, put S is equivalent to minus a, so this will become 1, this will become 0 minus a, so b will be equal to minus 1 by a. So further we can make this, so C of S can be written as, sorry, C of S can be written as a, okay, a divided by, that is, capital A is 1 by a into S, small a is 1 by a, minus 1 by a into S plus 1, S plus a, sorry. A and a gets cancelled, so C of S we can write as 1 by S minus 1 by S plus a. So that if we take the Laplace transform of this one, taking the Laplace transform, so C of t in time domain will be 1 minus e to the power minus at. So let's call it equation number 2. We had this, I think, equation number 1. Yeah. Okay, now afterwards we have to draw the graph and we'll explain it tomorrow, inshallah. This is valid for what? This is basically valid for t greater than 0. So tomorrow we have to draw the graph and we'll be explaining about the time constant, rise time, and settling time. If I think tomorrow we don't have a class, and we'll see in the next class. Okay, let me stop this.